Dear students, welcome to the first session of our chapter 11, P block elements. As we have learned the periodic table, we know that there are four blocks of elements: S block, P block, D and F block elements. Now in this chapter we will deal with the P block element. In P block element, we know that the last electron should enter the P orbital. As we know that the number of p orbital is 3. So the maximum number of electrons can be accommodated is 6. And there are 6 groups of p block elements in the periodic table, numbering from which all groups? Group 13 to 18. That means 6 groups are there which belongs to the p block element. It is interesting to note that the nonmetals and the metalloids exist only in the p block of the periodic table. The non-metallic character of elements decreases down the group. In fact, the heaviest element in each p block element is the most metallic in nature. This point you have to keep in mind that when we take the p block elements, the group when you are taking, the last or the heaviest element in each group will be most metallic in nature. Now let's see the position of the p block elements in the periodic table. We know that 18 groups are there. Among the 18 group, the first and the second group is said to be the S block. In between, the third to 12, it is there, which is said to be the D block element, and after that the 13 to 18 group is said to be the P block element, and down we have separately kept the 14 plus 14 elements, which is for F block. Let's see the electronic configuration of the P block elements, and the general outer configuration will be Ns2Np1 to Ns2Np6. Why? Because the 13th group will be having the configuration Ns2Np1. If we take the 18th group, we will get Ns2Np6. That's why in general it is written. Otherwise you can write Ns2Np1 to 6. This is the electronic configuration for p block elements. And according to this, we know that there are 6 groups in the p block element. So we can name the 6 families in the p block element as boron family, carbon family, nitrogen family, oxygen family, halogen family, and noble gas. So the first member of the group is said to be that family. And the electronic configuration of each family, it is mentioned here. That is Ns2Np1 for boron family, Ns2Np2 for carbon family, Ns2Np3 for nitrogen family, Ns2Np4 for oxygen family, Ns2Np5 for halogen family, and Ns2Np6 for noble gases. So this is about the electronic configuration of p block elements. Now let's see the first family, that is the boron family, which belongs to group 13. And this group of elements show a wide variation in their properties. Like boron is a typical non-metal, but aluminium is a metal but shows many chemical similarities to boron also. That means both the properties it is showing. Gallium, indium, thallium, and nihonium are almost metallic in character, or they belong to the metallic nature, and these are the heavy elements in the group also. The electronic configuration, just now we have seen that is Ns2Np1. Outer configuration only we are talking about. A close look at the electronic configuration suggests that while boron and aluminium have noble gas core, gallium and indium have noble gas plus 10 electrons, and thallium has noble gas plus 14 electrons plus 10 d electrons core. This is about the electronic configuration in the respective group. Now let's see the atomic radii of the elements belonging to 13 group. As we move down the group, we know that one extra shell is added, so the atomic radius is increase or it increases down the group. However, a deviation can be seen here in this group. That is, atomic radius of gallium is less than that of aluminium. And this can be understood from the variation in the inner core of the electronic configuration. The presence of additional 10 d electrons offer only poor shielding effect for the outer electrons from the increased nuclear charge in gallium. That's why the atomic radius of gallium is less than that of aluminium. Consequently, the atomic radius of gallium, which is 135 picometer, is less than that of aluminium, which is 143 picometer. Next is the ionization enthalpy among the p block elements. As we know that ionization enthalpy is the amount of energy required to lose an electron from gaseous atom. So here ionization enthalpy among the p block elements we will see. It decreases from boron to aluminium. Going down the group, it decreases. But according to the increase in size. But there is some discontinuity in the ionization enthalpy between the aluminium and gallium and also between indium and thallium, which are due to the inability of d and f electrons, which have low screening effect to compensate the increase in the nuclear charge. That is why there is a discontinuity in the ionization enthalpy. Next is the electronegativity. Down the group, electronegativity first decreases from boron to aluminium and then increases marginally. And it is because of the discrepancies, that is, noticeable difference in atomic size of the elements. And the last one is about the physical properties of p block elements. It is like boron, when we are saying it is non-metallic in nature. It is extremely hard and black colored solid. Due to very strong crystalline lattice, boron has unusually high melting point and rest of the members are soft metals with low melting point and high electrical conductivity. Gallium with unusually low melting point could exist in liquid state during the summer. Its high boiling point makes it a useful material for measuring the high temperatures. Density of the elements increases down the group from boron to thallium. So that we know that when going down the group, of course, what happens? The atomic mass increases. So the density of the element also increases going down the group. Thank you. We'll continue in the next session.